Now that we have finished our look at reversible nucleophilic addition to aldehydes and ketones, we're going to take a look at a couple of other reactions. In this video, we'll be looking at the Wittig reaction of aldehydes and ketones, as well as oxidation of aldehydes. The Wittig reaction is a way to make alkenes with complete regiospecificity. Keep in mind other ways that we've seen to make alkenes include dehydration, dehydrohalogenation, and Zaitsev's rule tells us that we're going to get the more substituted alkene as the major product, but still a mixture of alkenes at different locations is likely. With the Wittig reaction, we know exactly where that alkene is going to be. So the Wittig reaction involves an aldehyde or ketone reacting with a phosphorus ylide. So an ylide is a species that has a positive and a negative charge on adjacent atoms. So the molecule overall is neutral. But each one has an octet, and so the overall molecule is relatively stable. So the Wittig reaction is a coupling between an aldehyde or ketone and an ylide. And so this carbon of the carbonyl and this carbon of the ylide become an alkene. And a byproduct is triphenylphosphine oxide. And the phosphorus oxygen double bonds, these are very strong, and so the formation of this byproduct is actually the driving force for the overall reaction. So this is a carbon-carbon bond-forming reaction as well as a way to make alkenes. So here is the overall reaction, but let's look at some of the details. First of all, we have the preparation of the ylide. So this starts out with an alkyl bromide, and this is treated with triphenylphosphine, and this is a substitution reaction. So the phosphorus acts as a nucleophile, shares electrons with the carbon, and kicks out the bromine. And what we get is an alkyl triphenylphosphonium salt. And so this can be isolated. It can be recrystallized. This is a very stable salt. But then when this is ready to be used, then this salt would be treated with methyl lithium or some other strong base, and this acts as a base. It will grab off this proton, putting these electrons onto the carbon, and that gives us the ylide. This can also be drawn like this, as if there is a double bond between the carbon and the phosphorus. So you might see the ylide written either way. Once the ylide is formed, then it would react right away with a carbonyl containing compound. And basically this is going to line up so that the electron-rich carbon of the ylide is lined up with the electrophilic carbonyl carbon. And we can think of this carbon shares electrons with the carbonyl carbon, opening up these electrons, which are then shared with the phosphorus. And so what's formed is this oxaphosphatane intermediate. From here, this square is going to break down. We can imagine these electrons move here, these electrons move here, giving us the new alkene and the new phosphorus oxygen double bond. The good news is the triphenylphosphine oxide, this is the driving force for the reaction. The bad news is that it is really hard to separate that from your desired compound. Now, because we're thinking about the reaction where we have the carbon sharing electrons with the carbonyl carbon, we can again think of this like a nucleophilic addition. But the rest of the mechanistic aspects are not similar to the other reactions we have seen. So in this case, we have a symmetric ketone and a symmetric ylide. But what if one or the other isn't symmetric? What are we going to get? Let's say we carry out this reaction with benzaldehyde and this ylide, which is not symmetric. That will give us this alkene, But notice each alkene carbon is connected to two different groups, which means this product can be made as a mixture of cis and trans isomers. So one option is that the aldehyde and the ylide will line up like this. Let's say the methyl group is here and the hydrogen is here. We could imagine these electrons move here, these electrons move to the phosphorus, and that gives us as an intermediate this, and then we can picture these electrons giving us, here is our CH, double bond C, CH3, and H. So in this oxyphosphatane, we have both hydrogens on the same side. So in our product, both hydrogens are on the same side. This gives us the cis product. Alternatively, we could imagine this lining up in this way, where here is our ylide, and the hydrogen is here, and the methyl group is here. So these electrons move this way, these electrons move this way, and that will give us this intermediate. Here is the hydrogen, and here is the methyl group. And now we can imagine these electrons move here, these electrons move here, and that will give us the trans product. So in this intermediate, we have the hydrogen and the methyl on the same side. So here we have the hydrogen and the methyl on the same side of the double bond, which means our hydrogens are across from each other, or our big groups are across from each other, so this is trans. So unfortunately, the Wittig reaction will lead to a mixture of cis and trans. So the advantage of this reaction over other ways of making alkenes is that it is regiospecific. You know exactly where the double bond is going to be. The disadvantage, though, is that it is not stereoselective. Now, there have been a number of modifications or extensions, and these are all known as different named reactions. So there is the Horner-Wadsworth-Emmons reaction, there is the Masamune-Rausch modification of the Horner-Wadsworth-Emmons reaction. The names just keep adding up. And some of them are better at giving a majority of cis over trans. Other conditions are better at giving a majority of trans over cis, and so there are alternatives that can be used. But for now, we're going to focus on using the Wittig as a way to make not just a carbon-carbon bond, but a new carbon-carbon double bond. So let's try to think backwards and plan a synthesis of an alkene using a Wittig approach. So we want to think about breaking our alkene, and remember that our starting materials will include an alkyl halide and an aldehyde or ketone. So if we break it one way, then we can think of this as our carbonyl containing compound, and then the ylide would have to account for this piece of the molecule. So that would look like we have triphenylphosphine connected to the CH, CH2, CH3. So that these three carbons are these three carbons. And then if we work backwards further, then this is going to come from the triphenylphosphonium salt of this and let's say with a bromine counterion. And then finally, this comes from this, plus triphenylphosphine. So let's think of this in the forward direction. This is going to substitute here, kick out the bromine as a leaving group, and then this is going to be the counter ion. So we now have the phosphorus connected to the CH2, CH2, CH3. Next, this is going to be treated with a strong base, which is going to pull off one of these protons, giving the lone pair and the negative charge on the carbon. And now this carbon is going to react with this carbon, and then this oxygen will share its electrons back with the phosphorus. But in the end, what we're looking at is this carbon becoming connected to this carbon. Now we can also think of this, we're breaking the bond in the same place, but we can think of it from the other direction. So that this piece was the carbonyl containing compound, and this piece would have been the ylide. So that means we would have CH3, CH2, C double bond OH as our carbonyl containing compound, and then we would have the CH3, CH3 connected to the triphenylphosphine. So this is the ylide. The ylide could be made from this phosphonium salt with the Br minus as the counter ion, and then that could be made from this plus triphenylphosphine. So again, let's think of it in the forward direction. Let's put those lone pairs on there. So the triphenylphosphine will act as a nucleophile, share its electrons with this carbon, kicking out bromine as a leaving group, giving us this species with the bromine counterion. And then treatment with a strong base is going to pull off this proton, putting these electrons onto the carbon, giving us the ylide. And then this ylide is going to react with this aldehyde, where this carbon becomes double bonded to this carbon, giving us this product. So the Wittig reaction, despite the limitation of the lack of stereoselectivity, it is a very useful reaction. One other common reaction that will occur with aldehydes, not with ketones, is oxidation. So if we have an aldehyde, this can be treated with chromic acid to give a carboxylic acid. All right, so how does this work? Well, we have an aldehyde, and for a moment, let's just focus on the sulfuric acid and water. An aldehyde can react with water under either acidic or basic conditions to give a hydrate. That would look like this. Now, this hydrate is what actually gets oxidized to give the carboxylic acid. So remember a couple chapters ago when we talked about a primary alcohol, and it can be treated with chromic acid to give the carboxylic acid, or it can be treated with PCC or the Des-Martin reagent to give the aldehyde. The difference is not really because of the reagent, but it's actually because of the solvent. So PCC or Des-Martin, this can be carried out in dichloromethane or some other organic solvent, so there's no water present. And without water, we are not going to form the hydrate. So this reaction stops at the aldehyde. But when the primary alcohol is treated with chromic acid, well, it actually is converted to the aldehyde, which is then converted to the hydrate, and then the hydrate is converted to the carboxylic acid. So it seems like, oh, it's really fancy different reagents, but it's actually due to the solvent that there is a difference in reactivity between chromic acid or PCC. But if you're starting with an aldehyde, then chromic acid can be used to oxidize it up to the carboxylic acids. Ketones are not oxidized by chromic acid, so aldehydes can be oxidized by chromic acid to give the carboxylic acid. For ketones, treatment with potassium dichromate, sulfuric acid, and water, that's going to give you essentially no reaction because the ketones cannot be oxidized.